السلام عليكم. الحمد لله والصلاة والسلام على رسول الله أما بعد. The basic concept of internal interrupt, I think you might have taken in the class. Here on location 0, you have the reset vector. And on location 8, you have high priority interrupt vector. And on location 18, low priority interrupt vector. So these are the locations where the interrupt service routine will be stored. And what is an interrupt? Interrupt is simply a signal to the microcontroller which tells the microcontroller to stop running the main program and do something else. And what it has to do will be stored in one of these two locations. So you have high priority and low priority. The interrupt can be a signal inside the microcontroller itself, like a software generated interrupt, and it can be a signal, external signal from outside the microcontroller. Like for example, if you connect a button on one of the interrupt pins, that can generate an interrupt. And you can also connect a sensor or any other device which can send a pulse, and that can generate an interrupt. And a software interrupt is something that is from inside the microcontroller. For example, you have seen ADC, analog to digital converter. Now, when you write a program in ADC, for ADC, when you switch on or start ADC, like for example, when you set go bit and ADC starts, so after that, you have to wait until that go becomes 0, right? So this is what you have done before. Now, by using interrupt, you can enable ADC interrupt, and you don't have to wait for go to become 0. The program or the microcontroller can keep on doing something else, and whenever ADC conversion is completed, it can generate, the ADC module can generate an interrupt, and that will signal the microcontroller to go to one of these two locations, for example the high priority location, and copy the result of ADC from AD result registers and display them on one of the ports, for example. So any module, or most of these modules of microcontroller can generate their own software interrupts. For example, timer can generate its own interrupt. The UART, or the serial communication, can generate its own interrupt. So these are the different modules that can generate their own interrupts. So this was all internal inside the microcontroller. Now let's look at the pin diagram. Here, pin INT0, pin number 33, which has INT0 multiplexed on RB0. So this pin can generate an external interrupt. So you can connect a button or a sensor that sends a pulse on this pin, and that can generate an interrupt. Similarly, INT1 and INT2. So these are the different hardware interrupts that we have. 3 interrupts here on these 3 pins, and there is one more interrupt known as port B change interrupt. So these 4 pins of port B, RB4, RB5, RB6, and RB7, they can also generate an interrupt whenever there is a change on one of these pins. Okay, now we'll see from the interrupt section here which registers are used and how can we control them. Okay, so these are the registers You can see their names: RCON, which is reset control register, interrupt control register, interrupt control 2, 3, and then you have PIR 1, 2, 3, PIE 1, 2, 3, and IPR 1, 2, 3 registers. So these all these 10 registers, they are used to control the interrupt operation. Okay, so we'll see them one by one. The most important of them is the interrupt control register. Okay, this is the most important one. Okay, but before going here, let me show you the reset control register first. So there are two different interrupt priority levels: high priority and low priority level. Okay. If you want to use these interrupt priority levels, then we enable these interrupt priority levels by using this bit, IPEN bit of reset control register. Okay, so if this bit is 1, then you can assign some of the interrupts as high priority and some of the interrupts as low priority. So interrupt priority levels are enabled when this bit is 1. Okay, if you keep it 0, then all interrupts will have high priority. So you can simultaneously enable multiple interrupts, and some of them you can assign them as high priority and some of them as low priority. Okay, even if you enable multiple interrupts at high priority level, the first interrupt will be executed first. So whatever is interrupting the microcontroller first, that will be executed first. Okay, but if you are executing a low priority interrupt, and during that time a high priority interrupt occurs, then the microcontroller will stop executing low priority interrupt. It will go to the high priority, it will execute that first, and then it will go back to the low priority interrupt. So whenever you want to use the priority levels of interrupts, this bit should be enabled, or should be set 1. Otherwise you can leave it 0. Okay, the next register, or the most important register that we use here, is the interrupt control register. Again, you have 3 of them: interrupt control, and interrupt control 2, and interrupt control 3. Okay, so the first bit here, or bit number 7, is the global interrupt enable bit. So if you set this bit, then the interrupts are enabled. You can use any of these interrupts. If this bit is not enabled, then you cannot use interrupts. Okay, so this is the global interrupt enable bit. Then you have peripheral interrupt enable bit. So if you open the data sheet on your own computers, you can scroll down, you can see the details of all these bits. Okay, so peripheral interrupts are interrupts from these different modules, as well as interrupts, external interrupts. So peripheral interrupts can be, we'll see later on, there are PIE registers. So all these registers, whenever you use them, we have to enable PEIE, peripheral interrupt enable bit. Then the next 3 bits, TMR0IE, is a timer interrupt enable bit. Timer is a module that we see here. We'll see in the next labs. So timer can generate an interrupt. So if you want to use it, then this bit must be set to 1. Now similarly, we have INT0IE. Just few minutes ago I have shown you INT0 pin of the microcontroller. If you interface any sensor or any button there and you want to generate an interrupt on that pin, then this bit must be set as 1. Okay. Then next you have RBIE, port B change interrupt. So whenever there is a change on port B, one of the pins of port B, it can also generate an interrupt, and if you want to use it, then this bit should also be set to 1. So these 3 bits, they are IE bits. So you can see there, timer 0 IE, INT 0 IE, and RBIE. These are interrupt enable bits. Then you find similar names here: timer 0 IF, INT0IF and RBIF. So IF bits are the flag bits. Flag bits indicate that there was an interrupt. There was an interrupt from one of these peripherals or one of these pins. So if timer 0 interrupt occurred, then this IF bit will be set to 1. So that indicates to the microcontroller that there was an interrupt from timer 0. Similarly, INT0IF bit, this will be set as 1 whenever there is a signal change on INT0 pin. RBIF pin again, whenever there is a change on port B pins. So you can see the description here for all these bits given in the data sheet. Then the next register is interrupt control 2 register. So these pins, INT0, 1 and 2 pins. So you can have an external signal, which external signal changing from high to low or low to high. So the pulse can have a high to low pulse, a high to low edge, or a low to high edge. So known as rising edge or falling edge. So here, using these 3 bits, you can define whether the interrupt should occur on rising edge or falling edge. So these are the 3 bits to control that. This bit, IP bit. Now you have seen IE bit and IF bit. So this is an IP bit. IP bit is used to enable high priority level for this particular interrupt. So timer 0 IP is used to enable high priority for timer 0. Similarly, RBIP is used to enable high priority for port B. Okay, there is one more bit here known as RBPU. This is port B pull up enabled bit. Now, what is pull up? Previously, we have seen in the previous labs, whenever we connect a push button, that pin where a push button is connected, we connect an external resistor to power. You have seen that before. So instead of connecting an external resistor to power on port B or one of the input pins of port B, we can enable port B pull up by using this bit. So if this bit is 0, then it is enabled. So what happens is, internally, those input pins of port B, they will be connected to 5 volt or VDD. So if you don't connect an external resistor, that particular pin on port B will be read as 1. The input on those pins of port B will be 1, even without connecting anything on those pins. So this is known as pull up. They are pulled up to high volt or for VDD. So to enable pull up, you can see the bar on this name, RBPU. There is a bar on top. That means if it is 0, then pull up are enabled. If it is 1, then pull ups are disabled. And the next register here is interrupt control 3 register. So once again, you have INT2IP, the priority level enable bit for INT1 and INT2, and you have INT1 IE, INT2 IE enable bits for interrupt 1 and 2, and the IF bits here. These bits, they indicate that if there is an interrupt on these 2 pins, one of these 2 pins. Okay, so this is the basic, or these are the main interrupts that we have. Then we also have peripheral interrupts. So this way of interrupt control 2, and interrupt control 3 registers. Then we have PIR, PIE, and IPR register. So PIE register is peripheral interrupt enable register 1. So you have 1, 2, and 3. So in these registers, in these 3 registers, you find enable bits for different peripherals. So for example, here you have parallel slave port, read and write interrupt enable bit. Then you have ADC interrupt enable bit. So analog to, I spoke about the example of analog to digital converter. So if you want to use the interrupt on ADC module, then this bit should be 1. So you enable ADC interrupt by setting this bit. Similarly, RCIE is used for serial transmission and serial reception. So RCIE, TXIE. So these are the different peripherals that can generate an interrupt. So these are all inside the microcontroller. They are internal to the microcontroller. So you have PIE1, then you have PIE2, and then you have PIE3. So these are the different peripheral interrupt enable bits. Now you find a similar register known as PIR. So PIR has similar bits, but they are IF bits. So they correspond to the enable bits in PIE register. So you have seen bit number 6 here in PIE1 is analog to digital converter interrupt enable bit. So in PIR1 you find ADIF. So AD converter interrupt flag bit. Okay. So it says here the flag bit must be cleared in software. Actually, all the flag bits must be cleared in the interrupt service routine. So when you execute an interrupt, you have to clear these flag bits. They will be set as 1 to indicate that there was an interrupt. Then you have to clear them so that the next interrupt can occur. Okay. So you have PIR1 register for different flag bits. Similarly, you have PIR2 and PIR3 register. So these are the flag bits. And IPR register has the priority level bits for all these peripheral interrupts. So you can find ADIP given here. So if you want to use high priority for ADC, then this bit must be set as 1. Okay. And this part of this section here in the data sheet, it explains you regarding the INT 0, 1, and 2 interrupt. And there is timer 0 interrupt, port B change interrupt. Yeah. And what happens when interrupt occurs, context saving. You will see all these details in the class, how to use the interrupts and what are shadow registers and what happens to the W register and status register when interrupt occurs. So these details you will study in the class. So I'll explain you how a basic interrupt program is written. So if you open lab 6 sheet, you can find there is an example. There is an example in assembly as well as in XC8. Okay, so this is the lab 6 interrupt lab, and you can find the example given here. So when we write a program using an interrupt at origin 0, we cannot write our program or the main program at origin 0. So because if you write something there, then at location 8 you find interrupt service routine, so it will be overwritten. The program will be overwritten. So we cannot write our main program at location 0. So in this case, we will have multiple origin instructions in our program, as you see in the example given here. So what we do is we write our main program at some other location, for example, here at origin 100. So this is just an example. You can write at any other location in the program memory. So we start writing our main program in this example at location 100 in the program memory. So we write the label for main, and at origin 0, we simply write a jump instruction. We say go to main. So what happens is, as soon as the microcontroller starts running, it will execute this statement, go to main. It jumps to this location and it starts executing the main program. Now, when you have interrupts in the main program, you have to enable the interrupt and configure those interrupts as required. So in the main program, you have to set all the bits which are required for the interrupt, enable the interrupt and configure the interrupt. For example, here the first bit of the first instruction that which I have written here, BSF TRISB, INT0. So this example deals with INT0 interrupt. So we are configuring this pin as an input pin, okay, and then we clear the interrupt flag, the flag bit of this interrupt, which is in interrupt control register. Then we set whether it should be rising edge or falling edge using this instruction, BSF interrupt control 2, INT edge 0. So it defines the edge. Then we have interrupt enable bit for INT0. And finally, we enable global interrupts. So using these instructions, the INT0 interrupt is enabled and configured. Similarly, you can enable different register or different interrupts if you want. Now, what happens when this interrupt occurs? The microcontroller will jump to this location. It jumps to this location, origin 8. So we are writing the interrupt service routine here. So in origin 8, what do we have to do? We can have multiple interrupts on the same location. For example, at high priority, we may have enabled multiple interrupts. So the first thing that we do inside the interrupt service routine, so this part is known as the interrupt service routine. So here in this part, the first step is to check where was the interrupt from. So that is indicated by the flag bit. So that's why we are using the instruction BTF skip if clear. So we are checking whether this interrupt came from INT0. So if INT0 IF bit is 1, that means the interrupt was from here. So if this bit was 1, then we execute whatever we want. So in this example, we are simply toggling an LED. So we can write anything else, whatever, depending on your application. So this instruction will only execute when this interrupt bit was 1. So we may write some more instructions here for multiple interrupts. Then before closing the interrupt, we should clear the flag bits of those interrupts. So this instruction here, BCF interrupt control, INT0 IF, clears the interrupt flag bit. Okay. So we have to clear the flag bits for all the interrupts. Then we have the return instruction, and you can see this return instruction is slightly different from the return that we use in the delay loop in the subroutine. So this interrupt is RETFIE. Okay, return from interrupt with interrupt enable. Okay. So this is how we can write an interrupt program or interrupt service routine in assembly language. So similarly, there is another example for the C language for XC8. So once again, when we write the main function, so here we enable the input or output and clear the interrupt flag and configure the interrupts, like the edge here. Edge is configured as the rising edge, and interrupt is enabled here, and you have GIE as 1. So the global interrupts are enabled. In C, we can write name of the bit and then assign the bit directly. So we can write like this, interrupt. Okay, let me show you. We can write here interrupt control bits dot name of the bit, GIE, or we can simply write the name of the bit and assign the value there. So both these methods are applicable in C, in XC8. So TRISB0 is the name of bit number 0 of TRISB, and INT0 IF is once again name of the bit in interrupt control register. So this is how we configure the interrupt. So we can configure interrupt for any other module. Then how to write the interrupt service routine in XC8? So for that, we write this statement. So this is the keyword, void, then double underscore interrupt function, interrupt, and then you have brackets. So this is the keyword that you must write for any interrupt. Then This int0 is a name that you can assign by yourself. This is a name for the interrupt service routine that you can assign by yourself. So we write void interrupt brackets, and then you can give any name for this interrupt, and then again brackets. Then you can open the interrupt function. Then once again inside this interrupt function, we check the flag bit same way like how we have done in assembly. So we check the flag bit. If the flag bit of int0 is 1, and at the same time if int0 interrupt was enabled, so we are checking both these bits, whether it was enabled and whether the flag bit is 1. Then in this case, inside this if statement, inside the body of this if statement, you can write statements whatever you have to execute whenever there was an interrupt. So for example, the statement here is simply toggling the bit latch D7. So inside the body of this if statement, we can write the statements that should be executed when there was an interrupt. Okay, so before closing the if statement, we clear the flag bit of this particular interrupt. Okay, now the same example, I will modify this example here to include the Adc interrupt as well. So the first step is in the main function, we configure the Adc module. Now if you look at the data sheet once again, where is the ADIE bit? So I'll write Adc enable interrupts here after the int0, just before the global interrupt enable. So ADIE bit should be to enable Adc interrupt, and at the same time PIE bit should also be 1. This is because ADIE bit is inside one of the peripheral registers. So whenever you use an interrupt from the peripheral, PIE should also be enabled. And one more important point here is, before we enable any interrupt, we should clear the flag bit of that particular interrupt. So before we enable here if bit, we clear this flag bit. Why is it done? This is because when you write a program or main program, sometimes due to the execution of the program or due to any other signal change, suppose this flag bit of this particular was already set as 1, then what happens is, as soon as you enable the interrupt, there will be an interrupt at that particular time. So we clear the flag bit. Before enabling an interrupt, we have to clear the flag bit. So before enabling an interrupt, we have to clear the flag bit of that interrupt. Why is it done? It's because sometimes during the execution of the program, it is possible that this particular interrupt flag bit was already set. So if this bit was already set, and at that time if you enable an interrupt, immediately an interrupt will occur. So to avoid that, we clear the flag bit before enabling an interrupt. And once again in the interrupt service routine, we have to clear the flag bit of that particular interrupt before closing the interrupt. So in the same interrupt service routine, or in the same interrupt function, after this if statement, I'll write another if statement. This is for the Adc interrupt. Can you see the new if statement that I have written here? inside the same interrupt function. This will check if there was an interrupt from ADC. It will copy ADC result to a variable A. Now this variable, you have to, of course, you have to define this as a global variable. You can define it at the top of your program, like unsigned integer. So ADC result is copied to this global integer variable A. Here in C, you can copy high and low byte together by writing simply ADRES. So if you write ADRES without specifying high byte and low byte, it can copy 16 bits completely to this integer variable. It should be an integer because integer can hold 16 bits. Okay. And before we close this interrupt, we have to clear the flag bit of this interrupt. Is it okay now? So the flag bit is of ADC interrupt is cleared here, and then there is a return. So in C, we don't have to write return from interrupt RETFIE. So we simply write this function, and that will get translated to assembly when it generates the hex file. So ADC interrupt is written in this way. So one important point here, we are copying 16 bits of ADC result directly to unsigned integer variable A. So in this case, whenever we use 16 bits, instead of using left justified, we have to use right justified. The reason is we are copying 16 bits. We are using complete 16 bits. So when we use right justified, this will change, the data will change here. It should be like this. Okay. Yeah, the first line of interrupt is the same way like how it's written here. Void double underscore interrupt. Okay, this is the keyword of how we write interrupt in XC8. So double underscore interrupt function. And then this int0 is a name that you assign by yourself. You can give any other name here. You can say, for example, ADC interrupt instead of this. Or we can change, because now I have both int0 and ADC. So I can say int0 ADC. I can say both together in the name. So this is a name that you can assign by yourself. Then there are brackets again. So there are brackets here after double underscore interrupt, and there are again brackets after int0, the name of the interrupt. So this is the body of the interrupt. So in the main program, so this is what happens when there is an interrupt. It will execute. It will come here and it will execute here. So the main program is not complete. We have only enabled the interrupts here and configured the interrupts here. So after this, we'll have to write an infinite loop, a while loop that we normally write. So let's say while 1, and inside this while statement, or inside the body of this while loop, we can start ADC conversion. So AD control 0 bits dot go equal 1. So this will start ADC conversion. Now when we use interrupt, we will not wait for this bit to become 0. So we can simply tell the microcontroller to keep on doing some other work of any other function. So for example, if we have some LEDs connected, we can simply toggle those LEDs. So in the main program, as you see here, in the main program, the microcontroller is starting ADC conversion, and it is not waiting for ADC conversion to complete. It is doing some other work. So what happens when the interrupt completes, or when the interrupt occurs, or when ADC conversion is completed? It will simply go to the interrupt service routine. It will come here. It will come here, and it will execute these statements. So ADC result is copied to this variable A, and then the flag is cleared, and then it comes back. It comes back to the while state or while loop. Now let us see the block diagram of interrupts in the data sheet. So this is the interrupt logic given in the data sheet, and you can look at how different interrupts are processed by the microcontroller. So these are the peripheral interrupts. We have high priority interrupt generation and low priority interrupt generation here given here. So this is the IPEN bit, which enables high priority or low priority. Okay, and this is the peripheral interrupt enable bit and the flag bit given here, PEIE. As we see in the diagram here, these interrupts are the default interrupts. M0, RB, which is port B, INT0, INT1, and INT2. They do not belong to the peripheral interrupts. And other than these, the remaining interrupts, they belong to the peripheral interrupts. So if you want to use any of these interrupts, okay, so you have here the example given here is only for timer 1, okay, and it says additional peripheral interrupts. So any interrupt inside PIR or PIE 1, 2, and 3 registers, they belong to the peripheral interrupts. So if you want to use any of them, then PEIE bit should be enabled. Now let us look at the timing diagram of how interrupt or when interrupt occurs. So for any interrupt to occur, the global interrupt enable bit must be set as 1. The interrupt cannot function without enabling the global interrupts. So here in this example, we have the GIE bit, global interrupt enable bit, and port B change bit, RBIE, which indicates change on port B. So whenever there is a change on port B, whenever there is a change on the input pins of port B, it will generate an interrupt. So we enable RBIE port B change interrupt, global interrupts, and let us say our input pin is RB4, port B, pin number 4. So trace B of that particular pin must be 1. So at time 0, all these bits are zeros. At T1, we enable or we configure RB4 as an input pin, and trace B is 1 here. So this RB4 pin is configured as an input pin. At T2, there is a change on port B. So one thing that we must keep in mind is the flag bit of any interrupt. The flag bit of any interrupt is always set to 1 whenever the condition for that particular interrupt is satisfied. So here RB change interrupt occurs whenever there is a change on one of the input pins of port B. So here at this point at T2, there is a change, as we can see in the timing diagram, there is a change on RB4. As soon as there is a change, RBIF bit will automatically set as 1. The flag bit of any interrupt will be set to 1 whenever the condition for that interrupt is satisfied. So here RBIF bit is set to 1. But at this point, it will not cause an interrupt. There will not be any interrupt. Only the flag is set as 1, but there will not be any interrupt. The reason is GIE is still 0 and RBIE is also 0. At T3, GIE is 1, but again, there will not be an interrupt. There will be no interrupt here. At T4, RBIE is 1. So as soon as RBIE is set as 1, the microcontroller looks at GIE, whether it is 1, yes, this is also 1. And it also looks at the flag bit of that particular interrupt. So RBIE is 1 and the flag bit is also 1. So in this case, when these 3 bits are 1, the global interrupt enable, the port B change enable, and the flag bit of that particular interrupt is 1. So at this point, at T4, it will generate an interrupt. The microcontroller will generate an interrupt at T4. So whenever we have to find out whether an interrupt occurs or not, we have to look at these three bits: GIE bit, and the interrupt enable bit of any interrupt, and the flag bit of that particular interrupt. Okay. At T5 in the interrupt service routine, we clear the flag bit of this interrupt. So there will not be an interrupt at T5, and suppose we execute the interrupt service routine from T4 to T5 and we return back to the main program. Now at T6, there is no change in T6, and then in T7, once again at T7, there is a change on port B, on RB4. It goes from high to low. So there is a change on port B. So once again, the flag bit will automatically set as 1. The flag bit of port B change interrupt is set as 1. And the microcontroller looks at the enable bit for this interrupt. It is 1. And the global interrupt enable bit, this is also 1. So when it finds that the flag bit is 1, the enable bit is 1, and the global bit is 1, once again at T7, it will cause an interrupt. There will be an interrupt. So let's say we execute this interrupt service routine, and at T8, we clear the flag bit of RBIF of port B change interrupt, and we also clear the global interrupt enable bit here, just to switch off the interrupts. Now at T9, once again, there is a change in port B. At T9, there is a change in port B from low to high. So whenever there is a change on port B, it will set the flag bit here, as we see in the timing diagram. RBIF bit is set as 1, and RBIE bit is also 1. Interrupts are enabled. Interrupt for port B is enabled. The flag bit is 1. But since global interrupt enable bit is 0, it will not cause an interrupt. There will not be an interrupt at this point. So there will only be an interrupt at T7 when all the 3 bits are 1, and at T4. So these are the 2 points at where the interrupt will occur, or where the interrupt is executed. So this is the timing diagram of how interrupt occurs. In the activity, we are asked to interface a temperature sensor on AN2 and a button on INT2 pin of microcontroller. So in the main function of the program, in the main function, the microcontroller should continuously sample analog input. The microcontroller should take analog input on AN2, convert that to digital format, and display the result on the LCD. And using interrupts on INT2 and to pin, whenever there is a change on the button from high to low, whenever this button is pressed and released, that means whenever there is a change from high to low, we don't do anything. When it is released, when the button is released, toggle the state of RD7. So RD7 is set as 1, and this motor starts running. So once again, the microcontroller is continuously sampling analog input from the temperature sensor on AN2 pin, and the interrupts are enabled for INT2 pin. So whenever there is a change, when the button is pressed and released, there will be one pulse which has 2 edge, a rising edge, a falling edge, and a rising edge. So on the falling edge, we are not doing anything. So when the button is pressed, there is no change. We don't do any. The interrupt does not occur. And when the button is released. So there is a rising edge now from 0 to 1. So on this edge there will be an interrupt. So we have to write interrupt for this, and in the interrupt service routine simply toggle the state of RD7 pin, so it will switch on the motor. So once again in the next step, so once again if you press on the button there will be a falling edge. So the falling edge does not there is no interrupt on the falling edge, and if you release the button you have a rising edge, and in this rising edge the state of RD7 is toggled, and you can see the motor is stopped. The motor is stopped, and it is stopped here. You can see the RPM is decreasing slowly and it will stop. So this is the activity that you have to solve for lab 6. These are the steps that you need. These are steps given here that you need to solve this activity. So the first step here is to declare global variables for unsigned integer and character string. So unsigned integer, it will store the ADC result, and the character string to convert the number to string format and to display it on the LCD. Then we write the interrupt function. Inside the interrupt, use if condition to check whether the interrupt came from INT-IF bit. If this bit was set, this is the flag bit for INT2 interrupt. If this bit was set, then inside this if statement, toggle the output on RD7 and then clear the flag bit of INT2 interrupt. And then write another if statement inside the same interrupt. Write another if statement to check the ADC interrupt flag bit. So if the ADC interrupt flag bit is set, copy ADC result to the integer that we defined here, and then clear the ADC interrupt flag. Close the interrupt, and then write the main function. Inside the main function, initialize Adc module as we have done before, and use write justified, because we are using an integer and we'll be using 16 bits or 10 bits of ADC result completely. Initialize the ADC module, configure input and output using trace registers, configure or clear the flag bits of these two interrupts, INT2 and ADC interrupt, and configure falling edge for INT2 interrupt. Okay, it's written here falling edge, and you can define in the activity it was shown as in the example it was shown as a rising edge. So it's up to you. Just write in the comments what you are using, whether falling edge or rising edge. So configure whether falling edge or rising edge for INT2 interrupt. Then enable ADC interrupt, enable INT2 interrupt, enable PIE interrupt, verify the interrupt, and enable global interrupts. Then write a continuous while loop. Inside the while loop, start ADC by setting go bit. Okay. Then use sprintf statement to convert the integer, the global integer that you have defined above. Convert that integer to string format and display this integer string. Display this string on the LCD. Then close the loop and close the main function. So all these steps will help you in solving the activity. So this is all for lab 6. Assalamu alaikum wa akhiru da'wana alhamdulillahi rabbil alamin. Subhanallah bihamdihi, subhanakallahumma bihamdika, ashhadu an la ilaha illa anta astaghfiruka wa atubu ilayk.